In today's video, we're going to discuss electron configuration and quantum numbers. And before I go to the quantum numbers, we're going to start by talking about what the point of electron configuration is, what it represents, and what quantum numbers are supposed to represent. So when we're looking at any given atom or ion or let's say atomic particle, on the periodic table, then what we have to do is we have to be able to assess how many valence electrons it has, how many core electrons it has, and where these electrons are located, and what their energy levels are compared to one another. We need to be able to know which valence electrons are the ones that are being removed first, and then that will lead us into different periodic trends later on, such as electronegativity and ionization energy. And sometimes electrons aren't removed. Sometimes we need to know where the electrons are added to. And the chemical properties of many of the, if not all of the atoms and ions that can form are based on the electron configuration. So that being said, let's just take a quick look here and we can see that there are various different subshells and their capacity is different. So if we're going to discuss the different subshells, well, there are 7 different energy levels, which we will get to in a moment. And in each of those, there is a different combination of s, p, d, or f orbitals. Not every energy level has every single type of subshell. So let's move on to visualizing what the different subshells look like and the suborbitals within them. And so when we're dealing with the s orbital, as we mentioned in the quantum mechanics part of the atomic theory video that I had made, s orbital is a spherical shape and it holds 2 electrons. The p orbitals you can consider to look more like animal balloons that can exist in the x, z, and the y axes. So that would be left to right, up and down, and forward and backward. And then when we're dealing with the d orbitals, it gets more complicated, but you can imagine it will look more like a 4-leaf clover. I know that these images don't quite look like it, so depending on the models you look at, you'll see different variations of the electron cloud shapes and the way that they look. And the f orbital is too complicated to try to describe, so I'm going to leave that. But if you can see here, there are 7 different orbitals within the F subshell. So now that we've covered that, let's look at what some typical electron configurations look like. So here, when we're dealing with, let's say, nitrogen, oxygen, fluorine, and neon, you can see that there's a certain arrangement to the way that the electrons are written. So if we're looking at 1s, 2s, and 2p, you'll notice that even though each of these can hold 2 electrons, we don't immediately go and put another electron that's spinning the opposite direction until we've already filled all of the available energy spaces. And an important thing to remember about electrons, which this will be immensely important for the periodic trends, is that they all have negative charge. Therefore, electrons have a repulsive force against each other. So in the case of, let's say, 1s and 2s, well, 1s is the lowest energy level in this first n equals 1. We'll talk about the quantum numbers in a second. And so we do 1 up and 1 down. Then once that's full, we move to the second energy level where we have 2s, and that's the lowest subshell within that energy level. So therefore, we go 2s, 1 up, and another one with a downward spin. And then once we get here, we have to fill in each of these upwards first. And only after we filled all of those can we fill in a downward spinning or opposite spin electron within that first orbital in the 2p subshell. And this is according to a rule that's known as Hund's rule. Hund's rule. So this is a very good start for electron configuration. Another thing that I feel I really should point out, well, there's 2 things. So the first thing that I'm going to point out is that if you look at the periodic table is split into different blocks, which can help you figure out the electron configuration and where the valence electrons or the highest energy level electrons, the ones that are furthest away from the nucleus, are located at a glance without needing to write out everything at once. But it also helps you with writing out the electron configuration. So if we look here, this is going to be the highest energy valence electrons that H has. So it only has 1 electron because it's hydrogen, and so its core electron is its valence electron, And it doesn't need to meet the octet rule because there's only one 1s orbital, and that maxes out at 2 electrons. Therefore, it's already half filled when it has one. This is a large reason for why hydrogen behaves so much differently than the other alkali and alkaline earth metals, which are also in the S block, but have much different behaviors. So if we move on to this block over here, then we're going to notice that that is the P block, because once we go past 1s2 and then 2s2, which is beryllium, the next highest subshell in energy within the second energy level, which is 2, is going to be 2p. And so we're going to start to fill in. So this would be 2p1, and then this would be 2p2, and this would be 2p3. And then here we're going to come back around with oxygen, as you remember, and that's going to be 2p4, 2p5, and 2p6. Okay, so this would all be within 2p, and we've already filled in 2s, and we've already filled in 1s. So the electron configuration that I just wrote here would belong to neon. And it's important to remember that when we're trying to meet the octet rule, which if you pay attention to the second energy level here, there's 1, 2, 3, 4, 5, 6, 7, 8, right? So we meet the octet rule and we get to the noble gases. And if you look, all of the noble gases besides helium meet the octet rule, and that would be the most stable electron configuration. So once we move past the P block, then you're going to notice that the electron configurations, or the highest electron energies for transition metals, are going to be within the D block. And this is higher in energy than P and also leads to some interesting behaviors, which we'll talk about some exceptions to typical electron configurations in a moment, and it's specifically related to transition metals. This is a large part of the reason why transition metals can have a number of different ionic charges, +1, +2, +3, so on. This is another reason why transition metals tend to be very colorful. When they're in water, they tend to form interesting, pretty colors. And then another one that we're not seeing here, for some reason is not being visualized, is the F block, which is going to be a lot of radioactive elements. So if we're able to look down here, they included the F block, and as you can see, a majority of these have some electrons within the F block. So let's rewind a little bit and let's move to how do you fill in the electron configurations in the right order, because I know that that can be quite confusing. So this image right here is demonstrating what's known as the Aufbau principle. And so the arrows starting from the top will demonstrate that we fill in 1s, and then 2s, and then 2p, and then 3s, and then 3p, and then somehow 4s before 3d, and then 4p, 5s, and this is how you would write it. The likelihood of you actually needing to write this out on the test is very slim, but being familiar with this principle is definitely useful for understanding some of the things that we're going to talk about moving forward. So let's move on to the quantum numbers, because the purpose of the quantum numbers here, which we have N, L, ML, and MS, and we're going to describe each one in a moment, is that they serve as analogous to GPS coordinates for an electron. So if I want to describe to you with great accuracy exactly which electron I'm discussing within an atomic orbital, within an ion, whatever, surrounding the nucleus, then I want to use these quantum numbers because that's going to be the best way to go about it. So as we had discussed before, there are different energy levels, and these energy levels are represented by the principal quantum number, which is n. The possible values for n are whole numbers which are not zero. So the lowest one is 1, and it goes all the way up to 7. So as we go further away from the nucleus, we move up from n equals 1 to n equals 2 to n equals 3. So you can guess that each shell, each energy level is larger in radius than the previous. Okay, so it's further outside. If we go back to this table here and we look at the second quantum number, well, second quantum number is going to be the angular momentum or azimuthal quantum number, which can be kind of difficult to understand what exactly that means. But what we're going to point out is that the L quantum number represents the subshell or the shape of the orbital. And the possible values here may seem confusing, but really what it's saying is that the possible values for L depend on which n value we are dealing with. Well, in n equals 1, the only possible value that can happen is between 0 and n minus 1. So if n is 1, well, 1 minus 1 is 0. So the only possible value for L here would be 0. And 0, we'll come to find out, represents S. So here I'm going to write L equals 0. So when you see L equals 0, it's an S orbital. When we go back up here, just to continue this point, when we are in n equals 2, the possible values are between 0 and n minus 1. So what is 2 minus 1? Well, that is 1. So the possible values would be L equals 0 or 1. And so the 0 is representing S, and 1 is going to represent P. So if we come over here, we'll notice that the 2, so n equals 2, can have 0 and L equals 1 as the L values, the angular momentum quantum number values. So this would represent S and then P. If we're to discuss n equals 3, we're going to continue the same logic. There's 0, 1, and n minus 1. So we're also going to include D. So L equals 2 here. And then when you get to F, L equals 3. And that would only be possible if we were at least in the n equals 4 shell or greater. So let's go back here and let's discuss the third quantum number. So this is going to be based off of the angular momentum quantum number, and the possible values that will exist here are negative L to L, and everything in between that is an integer. If we're talking about L equals 0, and remember that that means that we're dealing with an s orbital, well, the only possible value for ML at that point is 0, because there's only one orbital within the s subshell that can hold electrons. So because there's only one option, as you see right here, the singular option for s is this. Therefore, anything that's in the s subshell will have the L equals 0 denotation. And then the only ML possibility, or the magnetic quantum number possibility, is also 0. If we extend this logic to the next subshell, so if we're talking about P, well, what did we say L was for P? Well, S was 0, so L is 1. Therefore, what are the ML values that we have? We have negative 1, we have 0, and we have 1. So just to continue this, why don't we do the same example for D? Remember that D is L equals 2 at this point, and so we have negative 2, negative 1, 0, 1, and 2. So the possibilities for ML, or the magnetic quantum number, are negative L to L, and that would also apply to F. So F was L equals 3, and that would mean that we have possible ML values of negative 3, negative 2, negative 1, 0, 1, 2, and 3. Hopefully that makes the point. So for the last quantum number, which we're going to discuss, let's go back to the table here. And the last one, since we were talking about spins, this is the perfect time to introduce the spin quantum number. So the way that the spin of the electron, whether it's spinning up or down or one way or the opposite way, we will denote that as positive 1/2 or negative 1/2. So if we were to go back to our examples of the electron configurations, then we can see if it has the spin upwards, then we can say the ms is equal to positive 1/2. And if it is downward, then it's equal to negative 1/2. And as we saw in the electron configurations right here. So before we wrap up, let me go down to this periodic table here just to point out a few of the exceptions to the electron configurations that the MCAT expects you to know. So as we had mentioned, once the 3p orbital is full, and that would be right here in the third period, which is the third row, we will fill the 3p orbital once we reach argon. And then we move to the 4s orbital as expected, because that is lower in energy than the 3d orbital, which would be starting from scantium going until zinc. And so what ends up happening is the exceptions occur when the d orbital is possibly half filled or fully filled. And I'll explain exactly what I mean by that. So if you look at scantium, well, that's going to be 3d1 because 4s2 is already full. Okay, great. Then we go to 3d2. All right, as expected, 3d3 for vanadium. And then suddenly we hit chromium and we go 4s1. So we already had the full 4s2 with vanadium, but then suddenly one more electron, and instead of being 4s2 3d4, it becomes 4s1 3d5. And this is because the repulsion that occurs within the 4s subshell, let's say, the repulsion that has when it was 4s2, so let's say we're going to draw the electrons that were like this, the repulsion that occurs between these electrons is greater in energy. So by spacing out these electrons within 3D, 5, so instead of being 4s2, chromium as well as molybdenum, if you look right here as well, are both happier with having the s orbital not being 2, but only being 1, half filled, and then half filling the 3D orbital as well, and making that half filled instead of only 4 and jamming 2 electrons within the s orbital. So this also occurs very similarly once we get to copper, silver, and gold. So very interestingly, in all of these cases, the s orbital is half filled and it prefers to fully fill and throw 10 electrons into the 3d10 orbital or the 4d10 orbital or the 5d10 orbital. And so these are different exceptions. So let's just say chromium, copper, silver, gold, and molybdenum. But the main ones that I want you to know are mainly chromium and copper, which the test will ask you about, but I would also recommend knowing silver and gold. I've never really seen molybdenum being asked about as an exception, but you never know. So I figured I would go over these with you just to demonstrate how when the d orbital can be half filled or fully filled, that certain exceptions to the rule can happen. But if you understood everything that we talked about so far, then you're at a great point with understanding electron configuration and the quantum numbers. So I hope that this was helpful in explaining how the electron shells are filled for any given atom and ion and the different energy levels that can be represented by the principal quantum number and the other quantum numbers that can tell us exactly which position each electron should have and how to describe them when asked. Thank you very much, and hopefully see you again soon.